Hey everyone, welcome to Ncert audiobook. Today we will see group 14 elements, the carbon family. Carbon, silicon, germanium, tin, lead and flerovium are the members of group 14. Carbon is the 17th most abundant element by mass in the Earth's crust. It is widely distributed in nature in free as well as in the combined state. In elemental state, it is available as coal, graphite, and diamond. However, in combined state, it is present as metal carbonates, hydrocarbons, and carbon dioxide gas 0.03% in air. One can emphatically say that carbon is the most versatile element in the world. Its combustion with other elements such as dihydrogen, dioxygen, chlorine, and sulfur provides an astonishing array of materials ranging from living tissues to drugs and plastics. Organic chemistry is devoted to carbon containing compounds. It is an essential constituent of all living organisms. Naturally occurring carbon contains two stable isotopes C12 and C13. In addition to these, third isotope C14 is also present. It is a radioactive isotope with half-life of 57-70 years and used for radiocarbon dating. Silicon is the second most abundant element on Earth's crust and is present in nature in the form of silica and silicates. Silicon is a very important component of ceramics, glass, and cement. Germanium exists only in traces. Tin occurs mainly as cassiterite SnO2 and lead as galena PbS. Flerovium is synthetically prepared radioactive element. Ultra pure form of germanium and silicon are used to make transistors and semiconductor devices. Symbol of flerovium is Fl. It has atomic number 114, atomic mass 289 gram per mole and electronic configuration Rn 5F14 6010 7s27p2. It has been prepared only in a small amount. Its half-life is short and its chemistry has not been established yet. The important atomic and physical properties along with their electronic configuration of the elements of group 14 living flerovium are given in table 11.3. Some of the atomic, physical and chemical properties are discussed below. Electronic configuration. The valential electronic configuration of these elements is Ns2Np2. The inner core of the electronic configuration of elements in this group also differs. Covalent radius. There is a considerable increase in covalent radius from carbon to silicon. Thereafter, from silicon to lead, a small increase in radius is observed. This is due to the presence of completely filled d and f orbitals in heavier members. 11.5.3 Ionization enthalpy. The first ionization enthalpy of group 14 members is higher than the corresponding members of group 13. The influence of inner core electrons is visible here also. In general, the ionization enthalpy decreases down the group. A small decrease in del H from silicon to germanium to Sn and slight increase in del H from Sn to Pb is the consequence of poor shielding effect of intervening d and f orbitals and increase in size of the atom. Electronegativity. Due to a small size, the elements of this group are slightly more electronegative than group 13 elements. The electronegativity values for elements from silicon to lead are almost the same. 11.5.5 Physical properties. All members of group 14 are solids. Carbon and silicon are nonmetals. Germanium is a metalloid, whereas tin and lead are soft metals with low melting points. Melting points and boiling points of group 14 elements are much higher than those of corresponding elements of group 13. Chemical properties, oxidation states and trends in chemical reactivity. The group 14 elements have 4 electrons in outermost shell. The common oxidation states exhibited by these elements are +4 and +2. Carbon also exhibits negative oxidation states. Since the sum of the first 4 ionization enthalpies is very high, compounds in +4 oxidation state are generally covalent in nature. In heavier members, the tendency to show +2 oxidation state increases in the sequence GeSnPb. It is due to the inability of Ns2 electrons of valence shell to participate in bonding. The relative stabilities of these two oxidation states vary down the group. Carbon and silicon mostly show +4 oxidation state. Germanium forms stable compounds in +4 state and only few compounds in +2 state. Tin forms compounds in both oxidation state. Sn in +2 state is a reducing agent. Lead compounds in +2 state are stable and in +4 state are strong oxidizing agents. In tetravalent state, the number of electrons around the central atom in a molecule, example carbon in CCl4, is 8. Being electron precise molecules, they are normally not expected to act as electron acceptor or electron donor species. Although carbon cannot exceed its covalence more than 4, other elements of the group can do so. It is because of the presence of d orbital in them. Due to this, their halides undergo hydrolysis and have tendency to form complexes by accepting electron pairs from donor species. For example, the species like SiF62- GeCl62- SnOH whole 62- exist where the hybridization state of central atom is sp3d2. Reactivity towards oxygen. All members when heated in oxygen form oxides. There are mainly two types of oxides, monoxide and dioxide of formula MO and MO2 respectively. SiO only exists at high temperature. Oxides in higher oxidation states of elements are generally more acidic than those in lower oxidation state. The dioxide CO2, SiO2 and GeO2 are acidic, whereas SnO2 and PbO2 are amphoteric in nature. Among monoxides, CO is neutral, GeO is distinctly acid, whereas SNO and PbO are amphoteric. Reactivity towards water. Carbon, silicon and germanium are not affected by water. Tin decomposes steam to form dioxide and dihydrogen gas. Lead is unaffected by water, probably because of a protective oxide film formation. Reactivity towards halogen. These elements can form halides of formula MX2 and MX4. Except carbon, all other members react directly with halogen under suitable condition to make halides. Most of the MX4 are covalent in nature. The central metal atom in these halides undergoes sp3 hybridization and the molecule is tetrahedral in shape. Exceptions are SNF4 and PbF4, which are ionic in nature. PbI4 does not exist because PbI bond initially formed during the reaction does not release enough energy to unpair 6s2 electrons and excite one of them to higher orbital to have 4 unpaired electrons around lead atom. Heavier members Ge2Pb are able to make halides of formula MX2. Stability of dihalides increases down the group considering the thermal and chemical stability. GeX4 is more stable than GeX2, whereas PbX2 is more stable than PbX4. Except CCl4, other tetrachlorides are easily hydrolyzed by water because the central atom can accommodate the lone pair of electrons from oxygen atom of water molecule in d orbital. Hydrolysis can be understood by taking the example of SiCl4. It undergoes hydrolysis by initially accepting lone pair of electrons from water molecule in d orbitals of silicon, finally leading to the formation of SiOH whole 4 as shown below. 11.6 Important traits and anomalous behavior of carbon. Like first member of other groups, carbon also differs from rest of the members of its group. It is due to its smaller size, higher electronegativity, higher ionization enthalpy and unavailability of d orbitals. In carbon, only s and p orbitals are available for bonding and therefore it can accommodate only 4 pairs of electrons around it. This would limit the maximum covalence to 4, whereas other members can expand their covalence due to the presence of d orbitals. Carbon also has unique ability to form p-pi multiple bonds with itself and with other atoms of a small size and high electronegativity. For examples, a few examples of multiple bonding are C double bond C, C triple bond C, C double bond O, C double bond S, and C triple bond N. Heavier elements do not form p-pi bonds because their atomic orbitals are too large and diffuse to have effective overlapping. Carbon atoms have the tendency to link with one another through covalent bonds to form chains and rings. This property is called catenation. This is because CC bonds are very strong. Down the group, the size increases and electronegativity decreases, and therefore tendency to show catenation decreases. This can be clearly seen from bond enthalpies values. The order of catenation is carbon very greater than silicon, very greater than germanium, almost equal to Sn. Lead does not show catenation. Due to property of catenation and p-pi bond formation, carbon is able to show allotropic forms. 11.7 Allotropes of carbon. Carbon exhibits many allotropic forms, both crystalline as well as amorphous. Diamond and graphite are two well-known crystalline forms of carbon. In 1985, third form of carbon known as fullerenes was discovered by S.W. Kroto, E. Smalley, and R.F. Curl. For this discovery, they were awarded the Nobel Prize in 1996. Diamond. It has a crystalline lattice. In diamond, each carbon atom undergoes sp3 hybridization and linked to four other carbon atoms by using hybridized orbitals in tetrahedral fashion. The Cc bond length is 154 picometer. The structure extends in space and produces a rigid three-dimensional network of carbon atoms. In this structure, directional covalent bonds are present throughout the lattice. It is very difficult to break extended covalent bonding, and therefore diamond is the hardest substance on the earth. It is used as an abrasive for sharpening hard tools, in making dyes, and in manufacture of tungsten filaments for electric light bulbs. 11.7.2 Graphite. Graphite has layered structure. Layers are held by van der Waals forces, and distance between two layers is 340 picometer. Each layer is composed of planar hexagonal rings of carbon atoms. Cc bond length within the layer is 141.5 picometer. Each carbon atom in hexagonal ring undergoes sp2 hybridization and makes 3 sigma bonds with 3 neighboring carbon atoms. Fourth electron forms a pi bond. The electrons are delocalized and over the whole sheet. Electrons are mobile, and therefore graphite conducts electricity along the sheet. Graphite cleaves easily between the layers, and therefore it is very soft and slippery. For this reason, graphite is used as a dry lubricant in machines running at high temperature, where oil cannot be used as a lubricant. Fullerenes. Fullerenes are made by the heating of graphite in an electric arc in the presence of inert gases such as helium or argon. The sooty material formed by condensation of vaporized CN small molecules consists of mainly C60 with a smaller quantity of C70 and traces of fullerenes consisting of even number of carbon atoms up to 350 or above. Fullerenes are the only pure form of carbon because they have a smooth structure without having dangling bonds. Fullerenes are cage-like molecules. C60 molecule has a shape like soccer ball and called Buckminster fullerene. It contains 26 membered rings and 12 5-membered rings. A 6-membered ring is fused with 6 or 5-membered rings, but a 5-membered ring can only fuse with 6-membered rings. All the carbon atoms are equal and they undergo sp2 hybridization. Each carbon atom forms 3 sigma bonds with other 3 carbon atoms. The remaining electron at each carbon is delocalized in molecular orbitals, which in turn give aromatic character to molecule. This ball-shaped molecule has 60 vertices, and each one is occupied by one carbon atom, and it also contains both single and double bonds with Cc distances of 143.5 picometer and 138.3 picometer respectively. Spherical fullerenes are also called buckyballs in short. It is very important to know that graphite is thermodynamically most stable allotrope of carbon, and therefore Delitzsch formation of graphite is taken as 0. Delitzsch formation values of diamond and fullerene are C60 are 1.90 and 38.1 kilojoule per mole respectively. Other forms of elemental carbon like carbon black, coke, and charcoal are all impure forms of graphite or fullerenes. Carbon black is obtained by burning hydrocarbons in a limited supply of air. Charcoal and coke are obtained by heating wood or coal respectively at high temperatures in the absence of air. Uses of carbon. Graphite fibers embedded in plastic material form high-strength, lightweight composites. The composites are used in products such as tennis rackets, fishing rods, aircrafts, and canoes. Being good conductor, graphite is used for electrodes in batteries and industrial electrolysis. Crucibles made from graphite are inert to dilute acids and alkalis. Being highly porous, activated charcoal is used in absorbing poisonous gases, also used in water filters to remove organic contaminators, and in air conditioning system to control odor. Carbon black is used as black pigment in black ink and as filler in automobile tires. Coke is used as a fuel in large and largely as a reducing agent in metallurgy. Diamond is a precious stone and used in jewelry. It is measured in carats. 1 carat is equal to 200 mg. 11.8 Sub-important compounds of carbon and silicon. Oxides of carbon. The two important oxides of carbon are carbon monoxide and carbon dioxide. Carbon monoxide. Direct oxidation of carbon in limited supply of oxygen or air yields carbon monoxide. On a small scale, pure CO is prepared by dehydration of formic acid with concentrated H2SO4 at 373 Kelvin. On commercial scale, it is prepared by the passage of steam over hot coke. The mixture of CO and H2 thus produced is known as water gas or synthesis gas. When air is used instead of steam, a mixture of CO and N2 is produced, which is called producer gas. Water gas and producer gas are very important industrial fuels. Carbon monoxide in water gas or producer gas can undergo further composition, forming carbon dioxide with the liberation of heat. Carbon monoxide is a colorless, odorless, and almost water insoluble gas. It is a powerful reducing agent and reduces almost all metal oxides other than those of the alkali and alkaline earth metals, aluminium, and a few transition metals. This property of CO is used in the extraction of many metals from their oxides ores. In CO molecule, there are 1 sigma and 2 pi bonds between carbon and oxygen. Because of the presence of a lone pair on carbon, CO molecule acts as a donor and reacts with certain metals when heated to form metal carbonyls. The highly poisonous nature of CO arises because of its ability to form a complex with hemoglobin, which is about 300 times more stable than the oxygen hemoglobin complex. This prevents hemoglobin in the red blood corpuscles from carrying oxygen round the body and ultimately resulting in death. Carbon dioxide. It is prepared by complete combustion of carbon and carbon containing fuels in excess of air. In the laboratory, it is conveniently prepared by the action of dilute HCl on calcium carbonate. On commercial scale, it is obtained by heating limestone. It is a colorless and odorless gas. Its low solubility in water makes it of immense biochemical and geochemical importance. With water, it forms carbonic acid H2CO3, which is a weak diabasic acid and dissociates into two steps. H2CO3 slash SCO3 minus buffer system helps to maintain pH of blood between 7.26 to 7.42. Being acidic in nature, it combines with alkalis to form metal carbonates. Carbon dioxide, which is normally present to the extent of 0.03% by volume in the atmosphere, is removed from it by the process known as photosynthesis. It is the process by which green plants convert atmospheric CO2 into carbohydrates such as glucose. The overall chemical change can be expressed as: by this process, plants make food for themselves as well as for animals and human beings. Unlike CO, it is not poisonous, but the increase in combustion of fossil fuels and decomposition of limestone for cement manufacture in recent years seem to increase the CO2 content of the atmosphere. This may lead to increase in greenhouse effect and thus raise the temperature of the atmosphere, which might have serious consequences. Carbon dioxide can be obtained as a solid in the form of dry ice by allowing the liquefied CO2 to expand rapidly. Dry ice is used as a refrigerant for ice cream and frozen food. Gaseous CO2 is extensively used to carbonated soft drinks. Being heavy and non-supporter of combustion, it is used as fire extinguisher. A substantial amount of CO2 is used to manufacture urea. In CO2 molecule, carbon atom undergoes sp hybridization. Two sp hybridized orbitals of carbon atom overlap with two p orbitals of oxygen atoms to make two sigma bonds, while other two electrons of carbon atom are involved in p pi bonding with oxygen atom. This results in linear shape with both CO bonds of equal length 115 picometer with no dipole moment. The resonance structures are shown below. Resonance structure of carbon dioxide. 11.8.3 Silicon dioxide SiO2. 95% of the Earth's crust is made up of silica and silicates. Silicon dioxide, commonly known as silica, occurs in several crystallographic forms. Quartz, cristobalite, and tridymite are some of the crystalline forms of silica, and they are interconvertible at suitable temperature. Silicon dioxide is a covalent, three-dimensional network solid in which each silicon atom is covalently bonded in a tetrahedral manner to four oxygen atoms. Each oxygen atom in turn covalently bonded to another silicon atom as shown in diagram. Each corner is shared with another tetrahedron. The entire crystal may be considered as giant molecule in which 8-membered rings are formed with alternate silicon and oxygen atoms. Silica in its normal form is almost non-reactive because of very high Si bond enthalpy. It resists the attack by halogens, dihydrogen, and most of the acids and metals even at elevated temperatures. However, it is attacked by HF and NaOH. Quartz is extensively used as a piezoelectric material. It has made possible to develop extremely accurate clocks, modern radio and television broadcasting, and mobile radio communications. Silica gel is used as a drying agent and as a support for chromatographic materials and catalysts. Kieselguhr, an amorphous form of silica, is used in filtration of plants. 11.8.4 Silicones. They are a group of organosilicon polymers which have R2SiO as a repeating unit. The starting materials for the manufacture of silicones are alkyl or aryl substituted silicon chlorides Rn SiCl4 minus N, where R is alkyl or aryl group. When methyl chloride reacts with silicon in the presence of copper as a catalyst at a temperature 573 Kelvin, various types of methyl substituted chlorosilane formula MESiCl3, Me2SiCl2, Me3SiCl with a small amount of Me4Si are formed. Hydrolysis of dimethyl dichlorosilane followed by condensation of polymerization yields straight chain polymers. The chain length of the polymer can be controlled by adding CH3 SiCl, which blocks the ends as shown below. Silicones, being surrounded by non-polar alkyl groups, are water repelling in nature. They have in general high thermal stability, high dielectric strength, and resistance to oxidation and chemicals. They have wide applications. They are used as sealant, greases, electrical insulators, and for waterproofing of fabrics. Being biocompatible, they are also used in surgical and cosmetic plants. 11.8.5 Silicates. A large number of silicates minerals exist in nature. Some of the examples are feldspar, zeolites, mica, and asbestos. The basic structure unit of silicates is SiO4 4-, in which silicon atom is bounded to 4 oxygen atoms in tetrahedron fashion. In silicates, either the discrete unit is present or a number of such units are joined together via corners by sharing 1, 2, 3, or 4 oxygen atoms per silicate units. When silicate units are linked together, they form chain, ring, sheet, or three-dimensional structures. Negative charge on silicate structure is neutralized by positively charged metal ions. If all the 4 corners are shared with other tetrahedral units, three-dimensional network is formed. Two important man-made silicates are glass and cement. 11.8.6 Zeolites. If aluminum atoms replace few silicon atoms in three-dimensional network of silicon dioxide, overall structure known as aluminosilicate acquires a negative charge. Cations such as Na+, K+, or Ca2+ balance the negative charge. Examples are feldspar and zeolites. Zeolites are widely used as a catalyst in petrochemical industries for cracking of hydrocarbons and isomerization. Example: ZSM5, a type of zeolite used to convert alcohols directly into gasoline. Hydrated zeolites are used as ion exchangers in softening of hard water. Okay, that's all for today. Thanks.